So, so this is basically what universe is made of: matter and energy. Uh, Now, so the classically, so we'll stay to the classical divisions. So classically, we divided matter and energy as two different things, and we say that something that can occupy space, has mass, is called matter, uh, and something that uh, does not occupy space uh, and does not have a mass, we called energy. And it was a distinct division uh, earlier, but uh, after Albert Einstein gave his famous equation E equal to mc square, which is the basis for nuclear energy. We now know that we can convert matter into energy, and energy can also get converted to matter. Uh, and, and, and that is basically a modern concept. Now, when you think of how the universe was created, the Big Bang, so earlier the concept is that, you know, uh, earlier there's only energy, okay, and suddenly something happened. We say the beginning of time, okay, something happened, there's Big Bang, and suddenly, uh, uh, you know, uh, this energy kind of radiated out into the uh, universe. Now, when I say universe, we really don't have any boundaries there, okay, um, and then gradually matter got created. So now we believe that matter, energy, and we know when we do the nuclear reactions that matter and energy are interconvertible. But for the purpose of this course, we'll take it for granted that they're two separate things, okay? And individually, matter is conserved, which is the conservation of mass. Okay, we learned about that in the previous chapter. And also there is the conservation of energy. Okay, so energy, like matter, cannot be created or destroyed. You can only interconvert from one to the other. So in this chapter, we'll first begin with matter. Okay, so we'll define matters. And when we define matters, we'll define matter in terms of atoms and molecules, okay, the micro constituents of matter. And also physically, when you look at matter, we can classify it into solid, liquid, and gas. And those are physical classification, the things that we see. And again, that classification is temperature dependent. So somebody who is living here on Los Angeles will say water is liquid, but somebody who is living in the poles will say that water is solid because that's what ice is and that's the temperature. So the physical state of matter is always temperature dependent, is relative to the temperature at which you are looking at it. And apart from this classification, if you look inside what matter is made of, we can again classify matter into elements, compounds, and mixtures. Okay. And these are very simple classifications, but things to keep in mind that what are the differences between them. So when you look at elements, they're only composed of one kind of atoms. Okay. Pure compounds. So there are pure compounds and there are mixtures. So pure compounds contain one kind of atoms and molecules. And within that, if it contains one kind of atoms, we call them elements. And that elements, the 92 elements on Earth, okay, and those elements appear in the periodic table. And they combine to form all the compounds, all the molecules that we see around us. So the compounds are basically contain molecules that are made by bonding of the atoms. And you can have pure compounds like water, but it contains the molecule of water, not the atoms. Uh, Now, mixtures are basically, they can contain various components there in varying ratio, and we'll look into it more closely, the differences between them. And then all matters has some properties, and we can divide matter into physical and chemical properties. Okay, so in this chapter, we'll look at what are the basic physical and chemical properties are and how you define them. Okay, so we want to distinguish between physical and chemical changes that happens. Okay, like melting of ice. What is that? Okay, um, and so on. And then there's the law of conservation of mass. So when you look at the law of conservation of mass, uh, um, is basically what we visited, in the previous chapter. So matter is conserved, and when you want to say that during a chemical reaction, mass is conserved, Dalton brought in the concept of atoms, and he said that during chemical reactions, mass is conserved because chemical reactions is rearrangement of atoms. So when you are rearranging something, nothing changes. So the number of players on the chessboard still the same, that changing place, and so mass is conserved. So up to 6 is about matter. Okay, and then 7 through 11 we have energy. So apply law so we are going to see that energy, as I said, there's a conservation of energy like mass, and uh, energy can neither be created nor destroyed. You can only interconvert between them, various forms of energy. We'll look at different units of energy and interconvert between them. Uh, Now, when you look at the chemical reactions, like you're burning gasoline and heat comes out, and there are other things that you have to heat. Okay, you have to give heat. So just the opposite process. So we'll see what these two processes are. We call them endothermic and exothermic processes. Now, this is about heat. And then there's temperature. What is the difference between heat and temperature? We often use that very loosely, but they're not the same term. Um, and within the temperature, we have various scales of temperature: Fahrenheit, Celsius, Kelvin. These are three that we have for this course. And we have to know how to interconvert between them. Okay, very, very useful tools, because we use Fahrenheit in our daily conversation, and science we use Celsius. So how do you convert between them without using Google? So, and then the finally we're going to relate energy, temperature change, and heat capacity, and that is how you can calculate the total amount of heat transferred. Okay, uh, so very, very, very useful chapter, and we'll use this concept in later chapters also, but relatively easy. So if you understood the previous chapter, how to do those calculations and measurements and things like that, this shouldn't be any problem. So defining matter. So matter is defined as anything that occupies space and has mass. And you can think of some examples that may be asked during the exam, but simple ones: anything, water, wood, plastic, steel, and they're visible. But again, there are matter that are invisible, like microbes, dust particles, the fogs. Okay, uh, or you think of tiny bacteria or viruses. So they're matter, but we cannot see them. Uh, Now, atoms and molecules are the ultimate, constituents of matter, all matter. So, in some substances like aluminum, uh, they exist as independent particles. In other substances like rubbing alcohol, water, they combine, the atoms combine to form molecules. And you can see this example here. This aluminum can, the individual atoms here. Whereas in this rubbing alcohol, they have these molecules which are formed by joining of the atoms. And these are chemical bonds that you cannot break. Now, we'll come back to this again. If you look at these molecules, each of these molecules have a definite composition. So it's quite different from mixing red ball and white ball and black ball and say this is a compound. So those are called mixtures because you can easily separate. each of the individual components. But here in this compound, we cannot. Now the states of matter. So physically, when you look at them through observations, we can physically classify matter into three states: solid, liquid, and gas. And we'll all know what they are. But we'll look at in the more scientific way, or the scientific definition. Okay. Uh, so this is ice, and everything is water here. Okay, water molecule. But you have the ice, you have the liquid water, and you have the gaseous one, the steam. Now, if you look inside, uh, in the case of ice, you can see that the molecules are very close together, and there is a definite arrangement of the atoms. They are basically tied down to a very fixed position. Whereas in case of liquid water, uh, the the water molecules are close, but not that close. So they can move past one another, giving the fluid property. Whereas in case of gas, they're wide apart. So the states of matter are basically, uh, you know, coming from how close the molecules are. Okay, so states of matter, the first thing we're going to look at is solid. So in solid matter, atoms or molecules pack close to each other in a fixed location. So that means they are very close, like the picture that you see here, and that closeness gives it the rigidity. So now when I say very close, they are close. That means they cannot move past one another. They have a fixed location, but they can move. They can vibrate. Okay, about that fixed location. Okay, and we'll talk about that more later. So there is motion there, but when it's vibrating, it's still keeping the center position the same. Okay, and that gives it the rigidity. So they have fixed volume, and they have a rigid shape. Okay, and you can think of some examples here. Uh, Now these are the types of solid that you will see. And if you look at the arrangement of the atoms, in the first case, there's a definite arrangement. We say long range array. Now this term, you please remember, okay? Uh, so they are called crystalline. So you might get a question like this, that what is a crystalline substance? They have a long range array, geometric pattern, okay, like salt, diamond, and you can see in case A, there's a nice arrangement of the atoms throughout the crystal. And then the other kind of solids, like where you can think of like spheres dumped on one another, and there is no different arrangement. So they are called amorphous. So two terms, crystalline and amorphous, very very important here. Okay, and you can think of glass, rubber, plastic as good examples of amorphous solids. So they are solid, but as you know, rubber. So if you take a rubber, um, or a plastic thing like a dough, okay, they are solid, but there is no different arrangement, so you can deform it very easily. Okay, there is no rigidity there. Now the next state of matter is the liquid. In the case of liquids, the atoms and molecules are close, but they are still free to move past one another, and that's give the fluid property of the liquid. And they have a fixed volume, but no definite shape. So that's the characteristic of the liquid. Okay, they assume the shape of the container, and you can think of a liquid from these examples here: gasoline, alcohol, water, mercury. Okay. Now, in the case of gases, they are free to move relative to one another. And one of the important property of gases is compressibility. So they are compressible. No other states of matter are compressible. And gases always assume the shape and volume of the container. Now, if you put everything together, this one slide is everything that you need. Okay. So this is the microscopic way we think about uh, the first two columns, solid, liquid, gas. So the molecules at the molecular level, the solids very close, liquids are also close, and the gases are far apart. But in the case of case of liquid, they're still free to move relative to one another. But in the case of solids, they are not. And the last three are the physical, properties: shape, volume, compressibility. So the shape of solids are definite, and the volume is also definite. But for the liquid, you can have any kind of shape, but the volume is still definite, and both of them you cannot compress. There is only with the gas that you can compress the, you know, compress matter. So, you know, very simple but very important definition here. And you might wonder that we talked about vibrations in the molecules. So, what keeps the atoms and molecules together? So there is molecular attraction, and as we move on to the other chapters, we'll see how these molecular attractions develop. So there must be some form of attraction to keep them together, and that relates to their chemical nature, okay, or the shape of the molecules, the bonding, and so on. So if you know enough chemistry, you can predict whether something would be solid, liquid, or gas. Okay, and so there's attraction, and there's also this vibration that is trying to move them apart. So there are two opposing forces that are playing there. Now, whichever predominates dictates the state of matter. So if the vibration, vibration is a form of energy. So if I give more energy in the form of heat, it will vibrate more. And so eventually a time will come when the vibrational energy will be enough to overcome the forces of attraction. And that is the point when a solid melts into liquid. And if you give more energy, the liquid molecules, even though there's attraction, they'll still vibrate, move around. The kinetic energy increases, and eventually they can overcome that attraction also and become gas. So it's all, to do with the temperature, the heat content in matter. So their matter and energy are intricately related. We cannot separate them actually. And the states of matter depends on the state of energy in that matter that you are looking at. Okay, now these are all physical classification based on observations. uh, Now we can also classify matter based on composition. These are what we call microscopic. That means you look inside. uh, So we can classify matter into pure substance and mixture. So a pure substance is composed of only one type of atoms or molecules. Only one type, but it can be atoms or it can be molecules. If it only contains atoms, we call them elements. And if it contains only molecules, we call them compounds. On the other hand, a mixture is composed of two of it can composed of more than two. It can be atoms or molecules or anything. Okay, but the difference between a compound and mixture is in a compound there's a definite proportion of the two elements that are coming together. But in the case of compound, they can be any. So there is no definite proportion. So you can think of water, being made of oxygen and hydrogen, but the number of oxygen molecules and the number of hydrogen molecules is fixed. So we call it the law of definite proportion, and that is true. That is true for all compounds. But we can also take oxygen gas and hydrogen gas and mix them together in any proportion. Then that is a mixture. So that is the difference between, a mixture of hydrogen and oxygen and water. Okay, and this law of constant proportion is at one time used to be the cardinal rule. Okay, when the chemists didn't have all these instruments that we have now. So if you bring water, to a chemist and ask him, can you please test that this water? He'll first check that it contains hydrogen and oxygen, and that they are in the ratio of 1:8 in terms of atoms. And that will prove that this is water. Uh, so these are compounds. So water is a compound. Um, Now within the mixture, as I said, you can have various proportions. The mixtures can be of two types: homogeneous and heterogeneous. Homogeneous means evenly distributed. Heterogeneous means uneven. Okay. Now you have to know examples from each of them. So evenly distributed, you can think of sugar, dissolved in water, sugar water, salt water. These are all homogeneous. What that means that if I take any sample from any portion of the liquid, it will have the same composition, is evenly distributed. Whereas if you take sand and salt and mix them together, they do not mix well. These are heterogeneous mixtures where you can physically separate them. Um, and also, you can think of like oil and water is a heterogeneous mixture. So if you look at matter then, in terms of what they're made of, we saw we can have elements, pure substances. It can be element. So what is an element? So element is a pure substance that cannot be broken down into simpler substances. So water, if you put some effort, and that has to be substantial effort, we can break the bond between hydrogen and oxygen in water and get hydrogen and oxygen from them. So basically, we can uh, break it down into simpler substances, but we cannot break it down any further. So once you get hydrogen and oxygen, if you want to break it down, you know, uh, we probably cannot. And if you try too hard, we'll basically destroy the atoms altogether. Okay. So compounds, on the other hand, are pure substances composed of two or more elements. Now, where the atoms of these elements are chemically bonded and they have a fixed definite proportion. So you have to know some examples from there: water, table salt, sugars. Okay, so water is a compound, sugar is a compound, table salt is a compound. Okay, but if you look at hydrogen, oxygen, copper, these are elements. Okay, uh, so memorize some examples from each of these classifications. So compounds can be decomposed into simpler substances. As I said, water, if you electrolyze water, you can still uh, decompose into hydrogen and oxygen, but you cannot decompose any further. Okay. So those are elements then. So those are elements that make up the water. So the law of fixed or definite proportion. So this, as I said, the important law. A compound is a pure substance composed of different atoms that are chemically united in fixed and definite proportion. So it cannot change. So if I have water, whether it is from Los Angeles, whether it is from New York, doesn't really matter. It'll still be water with the same ratio of atoms. Okay, the same elements and the same proportion. The mixture is composed of different substances, not chemically united. So if it is not chemically united, you can easily separate them, and we can easily separate them by physical means. And we'll see what physical means or physical property means. So basically, we can separate them without destroying them. So if you look at air, which is a mixture and has all these gases, nitrogen, oxygen, we can separate each of these gases. Okay, so they are physically mixtures. And this slide here basically summarizes everything that I just said. Okay, so if you remember this slide, you have everything. So this is the summary slide, okay, for matter. So you have the pure substances, you have the mixture. So within the pure substances, so what are pure substances? They have only one kind of atoms or molecules. If they have only one kind of atoms, we call them elements. If they have only one kind of molecules, we call them compounds. So what are molecules? Molecules are made up of atoms that are chemically bonded. Okay, and you can see some examples here of elements and compounds. So so apart from the pure substance, you can have mixtures, right? So mixtures have more than you know two kind of substances, two or more that are not chemically bonded. So a difference between a pure substance and mixture is that for a mixture, the amount of these components can vary. And within this mixture, you can have homogeneous mixture and heterogeneous mixture. So homogeneous means evenly distributed, like this cup of tea, okay, or sugar water, salt water. And what homogeneous means that if I take a portion, any portion of this liquid, it will have the same composition, like ocean water. Okay. Now heterogeneous means uneven. Okay, like salt and water, you really cannot dissolve evenly. Okay. Yeah, you have to know this classifications and examples from each of these classes. So like you'll be asked, what kind of mixture is this? Oil and water. So the answer would be uh, heterogeneous mixture. What is air? Is it a pure substance or a mixture? So think of what air is. It has components. What are the components of air? It has nitrogen, it has oxygen, and other like carbon dioxide a little bit, but mainly nitrogen and oxygen, little bit of helium. But again, can I separate them easily? Yes, I can. I can separate the oxygen and nitrogen easily. So air is a mixture. Now within the mixture, is it homogeneous or heterogeneous? Now, because you can separate it, it is a mixture. Now, within the mixture, you can have homogeneous. Homogeneous means evenly distributed. So all the components, so the composition of air, is it so like if you take air from one corner of a room and analyze it, and take air from another corner of a room and analyze it, okay, will it be the same? So homogeneous because any portion of my room, if I take air and analyze, it will have the same composition, evenly distributed. Everything in air is evenly distributed. So it's a homogeneous mixture. Just like if you think of salt water or sugar water, okay, ocean water. If you take ocean water in a tube, and if you take a little bit from the top and a little bit from the bottom of the tube, it will have the same amount of salt. So these are all homogeneous mixtures. Okay, now we'll look at properties of matter. Okay. Now, when you think of properties, is behavior, right? So there are two kinds of properties we can think of: physical property and chemical property. Physical property is the one that a substance displays without changing the composition. So, like color. Okay, so if you look at the color, nothing changes. It displays the color, and we say, oh, okay, this is red, this is yellow. Okay, so these are color is a physical property because when it is displaying that property, nothing changes. Okay, or if you say, uh, you know, uh, color or odor, the smell that you get, the characteristic odor of gasoline is a physical property. So color, odor, these are physical properties. Okay, because nothing changes when it's exhibiting that property. Now, if you think of flammability, that a substance is flammable. Flammable means, it catches fire and gives out heat. And uh, so when I want to say that gasoline is flammable, and gasoline want to exhibit that property, the gasoline changes. It burns out. That's what happened in a car, right? Burn out the gasoline. If gasoline would not burn, this world would be so much easier, right? We can keep using the same gasoline for the whole life. But it burns. It burns the carbon dioxide and water. So it just becomes a different substance. Its composition changes. So these are chemical properties. So when matter exhibit chemical property, it's the substance changes. The composition of the matter changes. Now, coming back to states of matter. So you see the states of matter, the matter that we saw is basically what they're composed of in terms of particles, atoms and molecules. But again, physically, they can be very close, these atoms and molecules, or substantially close or not close at all. So depending on the closeness, we can make some observations here. That matter when they're very close, they're rigid, we call them solids. We saw that. Okay. And when they're close but not enough close so that they can move past one another, we call them liquid. Okay. And then we have the gases. So this change from one state of matter, and that is depend on temperature, the amount of heat that you're providing. You can have solid water as ice, or you can have liquid water. Okay, so it depends on the energy content of matter. So this state change, we say state change of state, that is going from solid to liquid to gas. This transformation from one state of matter to another. These are called physical changes. These are physical changes because the actual composition of matter doesn't change. So water is still water molecule when you are forming ice. And you can get back the liquid water and nothing changes in terms of the composition. So these are all physical changes, the states of matter. So in a physical change, no matter changes its appearance, but not the composition. We saw physical properties in the previous slide. Now we are looking at physical change. So physical change is something when the composition is still the same. Okay, our observational appearance changes. So when ice melts, it looks different, but its composition is still same because it's the water molecule. So both are composed of water molecules. So melting is a physical change. And if you think of burning of gasoline, and gasoline changes to gas upon burning, not just gasoline evaporate out, but burn to something else. So that's the chemical change. Then tarnishing of copper coins. So copper, turns green upon exposure to air. What happens is copper reacts with the components of the air, especially oxygen and water vapor. Okay, and carbon dioxide. If there's a lot of carbon dioxide, it can form the carbonate. Okay, and forms a new compound. So the composition of the copper changes. Rusting of iron is a good example of chemical change because iron is no more iron. It basically got converted to the oxide of iron, which you call rust.
Rust.
Yeah, the rusting of iron. Now, how matter changes in chemical reactions. So when you do a chemical reaction, okay, when you do a chemical reaction, um, you have the reactants that are reacting and eventually giving you a product. So you can represent that uh, like this: reactants and with an arrow giving product. Now we'll see as we move on with our chapters that we can write the name of the reactant and name of the product, and eventually we'll be able to write the formula of the reactant and formula of the product, and that will constitute what we call a chemical equation. Okay. Now the basic thing about this, the reactant are reacting to give me product. Now, if you look at the amount of reactant, now the law of conservation of mass says that matter cannot be destroyed. So if I take a certain amount of reactant of certain mass, you know, I'll get the same amount of product. So matter is neither created nor destroyed in a chemical reaction. So that's the law of conservation of mass. So then some reactions, like I said, the nuclear reactions that happens in the nuclear reactors. Okay, uh, and also the basically the concept of the atom bomb, where substantial amount of matter basically gets annihilated, completely destroyed. Okay, to give energy. So so we are not getting that much amount of energy when not doing our chemical reactions. So for all practical purpose, we can ignore the small amount of change of matter that can happen due to the heat or the energy that is generated. So for this course, we'll consider that matter is conserved. Now, what that also tells you that the amount of reactant when you write a chemical equation should be equal to the amount of product. It cannot get lost. Okay. So if I add up all the reactant and if I add up all the products, they should be same. So if you look at this simple example here, so suppose that we burn 58 grams of butane in a lighter and it will react with 208 grams of oxygen to form 176 grams of carbon dioxide and 90 grams of water. So if you put them together, you have butane plus oxygen with an arrow, giving carbon dioxide plus water. So you have 58 grams of butane, 208 grams of oxygen, 176 grams of carbon dioxide, and 90 grams of water. So if you add up all the reactants here, you get 266 grams. If you add up all the products here, you get 266 grams. So, you know, nothing is destroyed or created during chemical reaction. And that will be the basis for our writing chemical reactions and balancing it. The balancing of chemical reactions that we'll do in later chapters. Okay. Now another thing that I want to point out here, that if I do not know any of the component, how much, I can easily figure out by doing the algebra. And you will definitely get this question, maybe during this exam, and again maybe during the final. So what happens is, as we learn more and more, we tend to use all these big formulas and equations, but often forget the simple thing. So I will give you the same question maybe during the final and ask you, and I know many of you will probably try to write formulas and do all kind of stoichiometry that you've learned by that time, and eventually get the answer, but maybe in a very long and hard way. But you know, it is very easy. If I say how much carbon dioxide is produced, just do the algebra. Use the law of conservation of mass. You do not even need formulas here, because uh, you add up the reactant, subtract, and it should be equal to the amount of the product. So if I tell you how much water is produced, you can tell how much carbon dioxide is produced. Just remember that. Okay, very easy way of solving this kind of questions. Just 10 seconds. Okay, now as I said, matter and energy are basically intricately related. And really, when you think of matter, the physical states of matter, it has to do with the energy content. So the behavior of matter is driven by energy. And if you think of what energy is, as I said, energy is something that does not have mass, does not occupy space. Basically, something that is not matter is energy. Okay, but and it is one of the major component of a universe, and at one point, and you can think of we really are still calculating. We have no idea. This open empty space is full of energy. That's what we say. Okay, so the universe that we look around has these planets and stars and things like that, but this empty space that you see within the universe is again filled with energy. And if you convert that energy, okay, to matter using Einstein's formula equal to mc square, that constitutes 90% of matter. So the energy equivalence that is around in the universe is 90%. It's a huge amount. So we really don't understand much of how nature works. But yeah, we really cannot ignore energy when we are talking about matter. Now, physicists also define energy as the capacity to do work. So work, and they define energy. What is definite, and they define work as if you are pushing a substance, okay, has a mass m, and you push it by d, let's say by distance d, then work is defined as force multiplied by distance. Okay, so that's the definition of work. So work is defined as a result of a force acting on a distance. We are pushing that a substance to a certain distance and you multiply the force to the distance, that's the amount of work you have done. Now, here you have a problem. So, as a chemist, so like if you are pushing a wall, okay, according to physics, because the wall didn't move, d equal to zero. So, work done is zero.
Okay.
But you have worked, and you have worked, you have spent energy. And what energy did you spend? You spend energy that is stored in our body as ATP, adenosine triphosphate, and that comes from the molecule glucose. So if you look at, so uh, since we'll be, later on moving on to biological field, we can discuss this that, the glucose that we eat gets broken down through glycolysis. Now, followed by, so glycolysis produces pyruvate that enters the mitochondria and performs what we call the Tca cycle. So, see, step by step, nature is trying to harness the energy. So, in the Tca cycle, it generates a high energy molecule, okay, called NADH. So, that NADH has electrons at very high energy level, and that electron gets donated to oxygen eventually to what we call the electron transport chain. And in doing so, it generates acid gradient across the mitochondrial membrane. So the mitochondria is double wall. It has two walls. And within these two walls, there's acid trapped. And this acid is basically pumped out as the electron is moving from NADH into oxygen. Now, why? So you have more acid on one side, less on the other. It's like a battery. It's nature's battery. So it's acid battery, if you put it that way. So you have more acid. Acid means H plus ions, and so you have more on one side. It's like holding the water with a dam, and then eventually it lets it flow. It lets it flow through a machine, enzyme machinery we call ATP synthase. It's literally a machine, and you can see as the uh, H plus ions flows through, it rotates and creates this phosphate bond in the form of ATP, and that is our energy coin. So when you are pushing the wall, you are you are breaking that ATP to ADP. That means you are breaking the phosphate bond. You are utilizing the bond energy. So yes, that's our. So even though physicists would say that we haven't done any work, but the chemist would come out and say, okay, he that student or he or she basically spent energy by utilizing the ATP molecules. The bonds contain energy. As we see as a chemist, is more like, you know uh, not to do with, even if we don't do work. So energy can be stored in terms of in chemical bonds, and we can harness that like a battery. Okay, it contains energy stored, okay, in the form of bonds, and that you can utilize through a chemical reaction. Okay, so understanding energy is critical in understanding chemistry. Very, very important. Okay, because the behavior of how they react, okay, what product you'll get. And as you learn more of this, you'll appreciate it more, that you can determine the product or how much product you'll get by calculations of energy. Okay, not in this chapter, but and not all in this course, but eventually you'll come across some of them. So the law of conservation of energy states that, like matter, energy is conserved. So you cannot destroy or create energy. You can only change it from one form to another. Okay. Uh, so like if you have a boiling water, that potential energy, you can run a turbine, which is mechanical energy from there, and the turbine in turn generates electrical energy. So you are converting one form of energy to another. You are not really creating a new form of energy or creating anything new. Like you are burning gasoline and you get heat, okay, and that is driving your car. So when you are burning the gasoline, you are utilizing the bond energy of gasoline. So that means there's energy in the bonds of gasoline, and that is getting broken, and that is coming out as heat. And that heat is eventually in expanding the gas, okay, mechanical energy, driving the pistons in a car, and you are moving, and the movement is kinetic energy. So all throughout, you know, we are basically dependent. We are not creating anything. Energy is already there. Now, if you think of that hydrocarbon, the bond energy in hydrocarbon, how did it come there in the first place? So we depend on sun for everything. That's the ultimate source of energy. And where we utilize the sun's energy and then convert into different forms. So the initial trapping of the solar energy is done by the plants. They generate the carbohydrates, okay, the bonds that form the carbohydrates. We eat those carbohydrates and we get the energy. So we are actually getting energized by the sun, okay, as the ultimate source of energy. So energy cannot be created out of nothing, and it does not vanish into nothing. Okay. So the total energy, if you think of mechanical energy, total energy is sum of kinetic energy and potential energy. Now, what is kinetic energy? Kinetic energy is the energy associated with motion, moving car, a moving rock, okay, moving water. So these are kinetic energy. And then the potential energy associated with its position, oftentimes composition, like stored energy, compressed spring is a potential energy. You lift a rock, that's a potential energy because of its position. If I let the rock fall, I can do some work with it. So energy is anything that has the ability to do work. Okay, falling water, just like falling water, the rock can do something. Okay, so these are potential energy. Now, the energy of the bonds stored in the matter, they are all potential energy. We call them thermal energy, the molecules. So we talked about atoms and molecules vibrating within matter. And this vibration, you know, is a form of energy. And that is what we call the thermal energy, the energy content in matter. Okay. And as you add more heat, it vibrates more because energy gets converted from heat to vibrational energy. Now, chemical energy is therefore a form of potential energy associated with the bonds, the position of the particles that compose the chemical system, how they are bonded, with whom they are bonded, the strength of the bond, and so on. So when you do chemical reaction is basically you break a bond and form a new one. So you can imagine that when you are breaking a bond, you need to give energy before you can form a new one. So energy is kind of intricately related with chemistry, okay, as also matter and atoms and molecules. Now, so we'll look at units of energy. Okay, so reactions are associated with energy, especially heat. In some cases, you can have light. Uh, so the units of energy, the two units or three basically we'll be dealing with, mainly two. So the SI, what is SI? SI means Standard International Unit. So we learned about SI units in the previous chapter. Okay. So the SI unit for energy is joules. Now, joule is actually the unit for work. Now, work and energy are interconvertible. So physicists, uh, can do calculations easily or make the calculations easier when they do in joule. So that's our SI unit. So, but the traditional unit of energy is calorie. Okay, is that traditionally that's the small c. The definition of calorie is defined as the amount of energy required to raise the temperature of exactly 1 gram of water by exactly 1 degree centigrade. So that's the classical definition of calorie. But they say unit is joule, and there's relationship between calorie and joule. So 1 calorie is 4.183 joule, and we can use that as a conversion factor. Now, nutritionists tend to use another conversion factor. Okay, so that conversion factor is the big cal. So 1,000 calories. So you can think of it as a kilocalorie. So that the oftentimes in the food levels you will see this big cal. The meaning of that is 1,000 small cal. Okay, so it's a kilocalorie, stands for kilocalorie. So we are going to use these three. Okay, now here in this, so these are the conversion factors that we'll be using. But here below, there's one more that we'll not be using. Okay, but it's good to know that kilowatt hour. So this called 1 unit of electricity or 1 unit of power. Okay, so so in a home when you say 1 unit or that's this many unit, okay, so the meaning of that is kilowatt hour, and 1 kilowatt hour is 3.6 10 to the power 6 joules. That's a huge unit, big unit. So we are not going to use too much of this, but mostly as chemists will be using largely the calories and joules. Okay, so here are some examples using this conversion factor. All right, so calorie big cal to joule. So a candy bar contains 225 big cal of nutritional energy. How many joules does it contain? So you have to basically, like similar to what we did in the previous chapter, you are just converting the unit from big cal to small cal and to joules, and each step has their um, you know each step has their own conversion factor. So this is the conversion factor for the first step and then the next step. But when you are doing it, remember that we are following the units. The previous units should cancel out and the final unit will remain. And these are defined quantities. This 1,000 calorie, 4.184, they depend exact. So do not attach a significant figure to them. Our significant figure will depend on the measured quantity, 225 big cal. So the correct answer is 9.41 in 3 significant figures. Okay. Now, energy, when you're doing a chemical reaction, energy, oftentimes energy is either released or absorbed. Now, when you think of energy is released, okay, why is energy released? That's because if you look at the case A, the reactant is at high energy. And when it's a reactant is at high energy, I'm talking about the bonds that make up the reactants. And you can add them up. And the reactants is at high energy. And the products is at lower energy. So now when the reactant become product, this excess energy is released because energy cannot be destroyed, and the energy gets released, okay, into the uh, uh, outside the system. On the other hand, if the product is at higher energy and the reactant is at lower energy, in order to go to the product, you have to give energy. Okay, so that energy is absorbed. So there are two terms that you must remember. Exothermic, exo means released, exo out, going out. So exothermic reaction means heat, here energy is released, and endothermic reaction means energy is absorbed. Now, having said that, uh, so let's say that you are burning gasoline and heat is coming out. Okay. So what is that? Exothermic or endothermic? Correct. Because energy is released, you get heat. So it's exothermic. On the other hand, um, let's say um, melting of ice. Is it
Oh,
exothermic? Is melting of ice
endo?
Endothermic,
Exothermic.
because heat is absorbed,
absorbing the energy.
right?
Yeah.
Yes. So the opposite, when you are uh, keeping water in the refrigerator and it has to become ice, that means it has to release energy. Why? Because water molecules are moving fast. It has to, so what the refrigerator does, it takes the energy from water, reducing its motion, and eventually it solidifies. So what it does with that energy that is taking out from the water, it throws to the outside. So that's why the energy, the region around the refrigerator, becomes hot because a refrigerator, that's the job of the refrigerator, it takes the heat from all the food that we are keeping there, including water, and then throwing that heat outside, okay, taking away the heat so that it freezes into solid. So this is heat. So that means heat, as you can see, is related to molecular motion. And when I'm saying that uh, the refrigerator is absorbing heat, what it is doing is taking the heat that is represented by the molecular motion. Okay, that's the kinetic energy, and taking them out as heat energy. Okay, so the ultimate source of that is molecular motion, and 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 when you think of heat, then if I take more matter, we'll have more heat content in there, like a bucket of water. Okay, so if you have a small beaker of water and bucket of water, definitely the bucket of water will have more heat. Okay, now what is temperature? If you look at the molecular vibrations that is happening in matter and how fast they are vibrating, this is the average. So the molecules in the beaker are vibrating at the same rate as the molecules in the big bucket. Okay, so they will have the same energy because the rate of vibration is the average kinetic energy is the same. Average kinetic energy per molecule is the same, but you have more molecules, so you have more heat. So there's a difference between temperature and uh, and heat. So you can think of uh, temperature as so you can have like the beaker of water and the bucket of water, both of them at same temperature, but the bucket will contain more heat because the total number of molecules is more. So heat is basically the sum total of energy, and uh, temperature represents the average kinetic energy, how fast the molecules are moving or vibrating. So the atoms and molecules are in constant random motion. Okay, uh, and that's what we call the thermal energy. And temperature is basically an average of that thermal energy. The hotter the object, the greater the random motion, the vibration. Okay, uh, higher the temperature. So temperature, uh, you know, so that means what happens is when it flows, so you can think of like a waterfall. The temperature represents the height of the waterfall, or whether it's going to fall at all. Okay, so heat is basically the water, and heat flows from higher ground, that means at higher temperature, to a lower temperature. Okay, amount of heat depends on the amount of water flowing, not on the height. Okay, so height just says how fast. Okay, we say potency. Okay, ultimately, if you want to calculate the total amount of water flowing, you have to basically do some calculations there, and that has nothing to do with the height of the waterfall. So the temperature, so heat, which has a unit of energy, is a transfer and exchange of thermal energy. Just like I said, the Fourier test, you know, reducing the kinetic energy of the molecules by taking away energy in the form of heat. Okay, so in the form of heat, um, so that's how energy stands per. And heat we can only measure when it's getting transferred. So if you know what is the temperature difference, we know how much matter is there, we can actually calculate the amount of heat that is getting transferred. So temperature, by contrast, is a measure of the thermal energy, not the exchange. It's the average, how fast the molecules are vibrating. That's it. Okay. So there are different scales of temperature, and the different scales, you know, uh, they were created in different parts of the world. And they have different stands. Like they are very comparative scales. Like when you say Celsius scale, somebody one day thought that, well, has to be somebody important. Uh, that, well, let's say uh, that water freezes, the temperature at water freezes, let's take it as 0, and the boiling water as 100. So it's kind of arbitrary. Okay, you have to have a base. They said let's take it as a base, like water is 0, ice, because it's a very common substance, and the boiling water is 100. And let's divide this gap in between 0 into 100 parts, and we call them 1 degree Celsius. Similarly, you know uh, other part of the world, and they said, okay, let's take salt water. Why salt water? Maybe they're thinking about how to help the fishermen. Okay, saturated brine used in many places for preservative and other things. So they said, let's let's call the uh, freezing point of saturated brine as 0 degree Fahrenheit, and the boiling water as 212 degree, and let's divide the region in between with 180 coefficients, and let's call it Fahrenheit. So it's defined by, and there are other scales also, but these are two important ones that we want to learn. So if you think of, and then there's a Kelvin, which is basically similar to centigrade. You have to just add 273 to it. So water freezes at 273 Kelvin and boils at 373 Kelvin. And we have water freezes at 0 degree centigrade and 100 degree centigrade. And in terms of Fahrenheit, uh, we can say that water freezes at 0 degree, not is 32 degree Fahrenheit, and water boils at 212. But we are all pointing to the same substance. Okay, only the numbers are different because we are using different unit. Now we can interconvert between them. Okay, and we have a formula. So in our case, we have to just learn the formula. So this is the case of ice. Okay, the water freezing, and this is the water boiling. But you see, the thermometer basically points to the same thing. Only our numbers are different. So we can use this as a conversion factor. Okay, and after you do that, you basically get these two important formulas. Okay, and these two you need to memorize. Centigrade to Fahrenheit, and you can use it back to get the Fahrenheit to centigrade, and then Kelvin. Okay. Now, so this is how we can calculate or interconvert between temperature scales. The next, we'll try to calculate heat. Okay, heat capacity, calculations of heat. So heat capacity uh, is the capacity, for any object of any size. So when you're heating it, um, and the amount of heat it requires to raise the temperature by 1 degree. So it can be of any size, okay, any mass. So that is called heat capacity. So if you take a rock and heat it, and the amount of heat it takes to raise the temperature by 1 degree centigrade. Okay. Now there's another term which is specific heat capacity. Okay, so that two different terms. So specific means per unit mass. So it's per gram So if you look at heat capacity, the unit of heat capacity will be joules per degree centigrade. Okay.
Yes.
Yeah, joules per degree centigrade. Now here we are not specifying the mass of the object. It can be of any mass. But if we specify per gram how much, then you can compare, right? So if you take a block of iron, and that is, let's say, 100 grams, and another like 10 grams, they will absorb different amount. They will have different heat capacities. But the specific heat capacity per gram will always be the same. So this has a unit grams per degree centigrade. Okay. Now, so when you have a specific heat capacity values, so that means we know how much joules is required per gram per degree centigrade. So if you multiply by mass, so if you have different mass of that object, so we'll have different amount of heat, and then if you multiply by how much degree, we raise the temperature. Okay, together if we multiply them, we get the total heat. So we'll be using this formula here, mc delta T. Okay, Q. So C here is the specific heat capacity. Okay, so it has the unit of joules per gram degree centigrade. And if you look at delta T, delta means difference, and that is always in degree centigrade. And the mass is in grams. So if you see, these grams and grams will cancel out. Degree centigrade and degree centigrade cancels out. And you'll have your answer in joules. Okay, so if you follow the unit. So always remember that this is the specific heat capacity. Now, here's the list of specific heat capacities here, the previous slide. Okay. So if you compare now, because they're all in 1 gram, right? So you had equal amount of each of these materials. Now you can see the lead only takes 0.128 joules to raise the temperature by 1 degree centigrade. And if you look at water, it's 4.184, many times more, 40 times, 35 times more. So water, to raise the temperature of water, we have to give 40 times more heat or 35 times more heat compared to lead. And you are trying to raise the temperature by the same amount. So this list is basically also follows what you call electrical conductance. So lead, gold, they're good electrical conductors compared to any of these metals below. So this is a kind of useful chart that you can use for our calculations. Okay. So you will have a bigger chart in the book. So here, in order to calculate then the total heat, we need the mass, we need the specific heat capacity, and that you'll get from the chart, or you don't need to memorize it. Only thing that you have to memorize is the conversion, that 1 calorie is 4.184 joules. That means by definition, water is 4.184 heat capacity. But otherwise, I'll give you these values. All you need to do is to multiply them. You need the delta T. Okay, and these are variables. So if any of these I don't know, I can always calculate. Not only that, if I'm given the total heat, I can calculate the delta T. Okay, so here is a question like, gallium is a solid at 25 degrees centigrade and melts at 29.9 degrees centigrade. So this is basically the melting temperature, and at 25 degrees centigrade. So this is your initial temperature Ti. So you form this small table because there are a lot of things written here. You write a small table here with the essential things that you need. So 2.5 grams, that's your mass. You have the Ti and Tf, final and initial temperature. So from here you can get the delta T, the difference of temperature, final minus initial. So delta T is always final, delta, the meaning of delta means difference, and we always do final minus initial. Okay. So we can calculate the delta T, and we can get this from the table. You just multiply them. So this given here, the specific heat capacity of gallium is this. Okay. So next step, we figure out the delta T. Now, when you're doing the delta, see TF minus TI, now we learned from the previous chapter that when you subtract, you keep to the least number of decimal places. Here the least number of decimal place is 1. So this is two significant figure now, 4.9. Okay. So when you multiply 2.5 with 0.372, and this is exact, okay, we can consider, though even though it's not exact because it's a measured quantity, somebody measured it for you. This is two significant figure, so answer must be in two significant figure. Okay, to raise the temperature from 25 degree to 29 degree, 29.9 degrees centigrade, you need to give 4.6 joules. Now, in order to actually melt, it will take more heat. So what happens is that when, so it's simple, identify, the mass, identify the delta T, okay, but when you do that, I'll always advise to have the small term, because sometimes these questions are very big with stories there, okay, which are unnecessary details. Write out the small table what you need, and don't go back and look at it again. Just make sure that you wrote this table correctly, do the calculations, and that is. Now, another thing is, here we calculate the Q. Now, you can see that we can basically, where I can ask you a question where I might say that, well, um, uh, I'll give you the Q, calculate the mass. You have the Q, you have the C, you have the delta T. Now you have to rearrange the equation. Now many mistakes happen when rearrangement of the equations. Now, if I want M, how will I do that? Okay, how to isolate the M from this equation if I need M? Okay, so you divide. So basically, you divide both sides by C delta T. Okay, so and if I were you, I would follow the steps. Okay, sometimes we make mistakes by trying to hurry things, but that only kills your time. Okay, so if I divide by the same amount, I am changing nothing. Okay, so you can see on the right hand side, this delta T, this delta T cancels out, M, C and C cancels out. What we have is M equal to Q divided by M, C delta T. C delta T. Okay, so always follow the steps in every equations. Okay, because you'll be doing this in other equations like gas laws and things like that, where you isolate the variable. Okay, and what I notice is that most of the mistakes come from here. So just try to cancel out and do it on both sides. Okay, and show your calculations. So if there's anything problem, you can go back and look at it when you write every steps. Okay, so you can also find them. You can find delta T. If I want to find delta T, then you do the same. You divide by the rest of the things. Okay, so you can also find delta T. So any of these variables can be obtained given the others. Okay, but we'll practice some problems here.